let's talk about vector addition. You guys have already been doing vector addition. We've only done it in one dimension, and we're going to go ahead and we're going to move into two dimensions. Now, the biggest thing you have to pay attention to with adding vectors is direction matters. You can only add vectors that are in the same direction or in opposite directions. So if I have these two vectors, I'm actually going to draw this one just a little bit longer. Then what I have is, let's say this is a 5 Newton force acting to the right, and this is, say, a 3 Newton force acting to the left. What would be the resultant of these two vectors, or the sum of these two vectors? Well, you guys would say the net force is equal to, we need to establish a positive direction, so let's say positive is that way. We'd say 5 newtons plus a negative 3 newtons, which equals 2 newtons. Well, why does that work? That works because vectors don't care where they're at. So graphically, what we're really doing is we said, okay, we started with this 5 Newton vector over here. And then we also had this 3 Newton vector over here. And when we added them up, essentially what we did was we said, okay, here's my 5 Newton vector. And from that, I have this 3 Newton vector. And I'm going to put it right here so I can see what it does. Well, it undoes some of what this vector does. And what I'm left with is just this little spot from the beginning of the first vector to the end of the second vector. And whatever that is, that's my resultant. And that's my 2 Newton vector that I was left with. Okay? So that's what we did. We can do the same thing in 2 dimensions, but we have to be careful because we can only add vectors that are in the same direction. Right? When we have a cart sitting on a track, we don't try to add the force of the string to gravity because gravity is trying to pull it down, which is completely independent from the force that's trying to pull it right. And so when vectors aren't in the same direction, we can't add them together. We have to find the parts that are in the same direction and add those together. So if I have an object that's sitting here and I have 2 forces acting on it, let's say I have one force that's acting completely in the x direction. It's trying to make it go this way. But I have a second force that's also trying to make it go in the x direction, but also trying to make it go up a little bit. Maybe it's that one. Okay? So I'm going to label these. I'm going to say this is F1, and I'm going to call this one F2. And I want to know what is F1. I want to know F1 plus F2. So I want to know the net force. Well, I can't just add up F1 and F2 because F2 doesn't pull in the same direction as F1. But some of it does, right? Because if F2 wasn't here, F1 wouldn't be as effective as pulling it to the right. So we've got to find the components or the parts that act in the right direction and add those. And we're going to do it just like we did before, okay? When we slid the one vector over to the other. So I'm going to take F2 and I'm going to slide it over here to the end of F1. Okay? Now I know my resultant vector then, or the sum of those two vectors, is actually this thing right here. Okay? So let me grab F2 and move my label with it. And so that's F2, and that means that this thing right here, this is the sum F1 plus F2. Well, I want to know its magnitude and its direction. And so to do that, I have to find what this thing is. Well, I look at that triangle. It's not a right triangle. I can't do a lot with that. I don't know what to do. So I'm going to go back to what I do know. I do know about components of vectors. And since we can establish our reference system however we want, I'm going to say vertical is positive in the y, and I'm going to say this horizontal direction is positive in the x, and then I'm going to find the parts of F2 that pull in those directions, because then I can deal with them. So let's see. I'm going to find F2 in x. I'm going to draw that one in green. Okay, and so that's the part of F2 that's over here, right? That's the x component of F2. And then I'm going to find the y component of F2. Let's draw that one in blue. And that's the part of it that goes vertical. And now, if you look at this, what I have is actually 2 things I can add together. Because F1 is pulling only in the x direction, I want to look at the components of F1 in the x. The component of x1 in x is F1. The component of F1 in y is 0. Okay? Well, F2, the component of F2 in x is this green section of the line. I'm going to call this F2x. Its component is whatever F2 is times the cosine of that angle, because that's the angle that's adjacent to Fx. Okay? So this is F2 cosine of whatever the angle is. And then this side would be, of course, F2 sine of whatever that angle is. Okay? F2 sine of that angle. Now, if you look at this, what I really have, and I'm going to pull this out of the way just so you can see it, is a triangle that has a right triangle, because these are the x and y components, that has the x's in the same direction, so I'm just going to add those straight up. So I can add x's there in the same direction. So I could say, all right, so then the resultant's x component is f1 plus the part of f2 in x. And the resultant's y component is the part of f1, 0, plus whatever f2 is in y. And then this whole triangle talks about this whole resultant force. So I can actually say, oh, f1 plus f2, the resultant, according to the Pythagorean theorem, is the square root of the x parts plus the y parts squared, right? That's just the Pythagorean theorem. And then if I want my angle for the resultant, okay, I can say that the angle is equal to the sine or the tangent or cotangent or whatever I want. I guess I'm going to use arctangent or the inverse tangent of the y parts over the x parts, just like before. So by using the components of a vector, we're able to add those together. There's one more thing I want to talk about. Before, we had forces that acted in opposite directions, and we could have balanced forces if they were the same. And what we said is, if that's the case, if this was F1 and F2, and those things add to 0, we said they're balanced, so net force equals 0. Then we said F1 plus F2 equals 0, and that's because F1 is exactly the opposite of F2. That's what that negative is, right? It's pointing exactly the opposite direction. Does that still work in the two-dimensional case? Well, sure it does. We just have to pay attention to what's going on, right? If I have a vector that's here, and let's say this is 27 meters, and the angle it's at is 30 degrees, what's the opposite of 27 at 30 degrees? Well, opposite means it's got to go 180 degrees away from it. It's got to pull this direction. So the opposite of 27 meters is 27 meters at 210 degrees because they're separated by 180. The other way you can write that is negative 27 meters at 30 degrees, just like we could before. These two things are exactly the same. Not equal and opposite, they're the same. They're both pulling all the way. This angle is 210, so they're 180 degrees apart. And negative means in the opposite direction. So if this is 27 meters at 30 degrees, this is 27 meters at negative 27 meters at 30 degrees. Okay? So those relationships still work. Plus and minus still mean opposite of each other, but now we're going to say opposite also means 180 degrees different.